Section 7.4 is the lengths of curves. So let's look at an example of a length of a curve and see what we need to do to find that length. This is an example of the sine curve, but for any curve in general, to find the length, we are going to use small segments, just like we do when we do rectangles. To find small areas, we're going to use small line segments to find length. And any line segment on a curve can be approximated by taking the difference between the two x values, the difference between the two y values, and using Pythagorean. So the square root of x squared plus y squared, those side lengths, will give us an approximation for this curve. As with everything we've done in calculus, we're going to make those curve lengths shorter and shorter. So if we partition any particular interval, they chose 0 to 2 pi, because again they're using sine, into intervals so short that the pieces of the curve lying directly above the intervals are nearly straight. So we talked before about local linearity. So as I make these segments shorter and shorter, they are becoming almost identical to the curve itself. Each arc is nearly the same length as the line segment joining its two ends. The length of the segment, not the actual curve, is the square root of delta x squared plus delta y squared. Now, continuing on with our normal progression, if we take the sum of all of those little tiny side lengths, or little tiny segment lengths over the entire partition, that will approximate the length of the curve. So we're going to change this using some Riemann sums. Now take a look here at what they've done. I'm going to do it step by step myself. So they've taken this square root of delta x squared plus delta y squared, and they've multiplied it by delta x over delta x. Now, they've then taken and put all of this under the square root. So delta x is the same as the square root of delta x squared. This delta x remains on the outside. Now, dividing both pieces by delta x squared, we then come over here and get the sum of the square root of 1, delta x squared divided by delta x squared, plus delta y over delta x squared. That, when we change it into integral form, is the length of the segment from A to B of the square root of 1 plus, I'm going to rewrite this in our familiar dy dx squared dx. So this is what we're going to do to find lengths of curves. Let's do one. We'll go ahead and do the sine wave from 0 to 2 pi. Whoops. So y equals sine x is our equation. I need to get dy dx for my formula, which in this case, is cos of x. And I'm going to do this on the interval from 0 to 2 pi. So using my formula, the integral from a to b of the square root of 1 plus dy dx squared dx, I'm going to substitute my 0 to 2 pi, the square root of 1 plus my derivative, cos x squared dx. Throwing this into the calculator using our integration, we get 7.6404. So this is the formula we're going to be using. You do have to memorize it. Here it is again. If a smooth curve begins at AC and ends at BD, with A being less than B and C less than D, and it must be a smooth curve, and it has to be continuous. We'll talk about that in a minute. Then the length or arc length of the curve is, this is the one we just used. Sometimes we have to flip it and use dy segments, and we'll talk about when that happens in one of our examples further on. Okay? All right, so let's do one. Find the length of the curve y equals x squared for x from 0 to 1. I want you to try this on your own. Remember, you've got to find dy dx first, and then see what you come up with, and then restart the video. Okay, dy dx is 2x. Our length, therefore, is the integral from 0 to 1 of the square root of 1 plus 2x squared dx. If you want to simplify this, you can, but this is going to be a calculator evaluation, approximately 1.479. All right, let's try a couple of situations that we have to do a little bit of fidgeting or fudging to get it to work. So the length of the curve y equals x to the 1/3 between -8, -2 and 8, 2. Well, this is the cube root, so this function looks like this, and we're going from -8, -2 to 8, 2. So if I was integrating this in little small segments, I would want to integrate from -8 to 8. My problem is that right here, I have an undefined derivative. So dy dx, which is x to the 2, taking the derivative, -2/3, right? When I do this, I get an x to the 2/3 in the denominator, and that is undefined at x equals 0. So, oh wait, I'm sorry. I'm still trying to antiderivate. My bad. Bring down the 1/3. There we go. But still, I'm going to end up with this function with a undefined value at 0. So dy dx is undefined at 0, so I cannot integrate across the interval -2 or -8 to 8. However, if I rewrite this, so I'm now going to write it as x equals y cubed. Now dx dy, not dy dx, dx dy is 3y squared. Okay, so let's look at this into our formula. We're going to take the length is this integral, and this time, since I'm going along y's, I've got to go from y to y, so -2 to 2 of the square root of 1 minus 3y squared dy. And if I put that in my calculator, I will get approximately 17.2606. So we have to watch out for that derivative if it is undefined anywhere, in other words, vertical asymptotes or vertical tangents somewhere in the curve, we have to flip it around. When we flip it, we're fine because this then becomes a horizontal. The derivative there is 0, and we can go ahead and calculate. Okay, the other thing we have to look for is getting around a corner. So let's look at this curve. This curve is the absolute value of x plus 1 from -2 to 1. This is an absolute value that has shifted to the left 1 unit. At -2, it equals 1. At 0, it equals 1. At 1, it equals 2. The derivative is undefined at this corner because the derivative from the left is -1. The derivative from the right is +1. So therefore, there is no derivative at -1. Let's look at this function as a two-part function. We all know, I hope, that we can write absolute values as a piecewise function. When x is less than -1 for this function, we use absolute value, which when the inside is negative means we want the opposite. So -x minus 1 when x is less than 1. And since anywhere where x is greater than or equal to -1, the function is positive or 0, we can use the function as is. So I'm going to break this down into two pieces. Go ahead and go to the next page so I have a little more room. got y equals negative x minus 1 for all x less than negative 1, and x plus 1 for all x greater than or equal to negative 1. So I'm going to integrate in two parts, from negative 2 to negative 1. Draw a picture again. I want this whole interval from negative 2 to 1. So from negative 2 to negative 1, I'm going to use this function. So dy dx for that top function is simply negative 1. The square root of 1 plus negative 1 squared dx. And I'm going to add to that the integral from negative 1 to 1. And my dy dx for this top function is positive 1. Now it just so happens with this function, even though I broke it into two parts, I end up with the same integral for both. That will not always happen. Let's do these separately. The antiderivative here is root 2x from negative 1 to negative 2 plus root 2x from negative 1. Oops, I'm sorry. Negative 2 to negative 1. I knew that didn't look right. All right, negative 2 to negative 1, and then negative 1 to 1. So this would be plugging in negative 1. I would have negative root 2 minus a negative 2 root 2 plus top root 2 minus a negative 1 root 2. So let's get rid of all these negatives. Negative root 2 plus 2 root 2 plus root 2 plus another root 2. Two of those will cancel, and I'll end up with 3 root 2. So that is the length of this curve. Now, since these were straight lines, I could have done this using some of our other tools. So let's redraw this picture. Whoops. There we go. And let's take a look at these as line segments. So this is part of this right triangle, side length 1 and 1, so that length is root 2. This is part of this triangle, side lengths 2 and 2, so 2 squared plus 2 squared is 8, so this is root 8. If I add those lengths together, I have root 2. Sorry, let me go back. It's not going to let me. Yeah, it will. Okay. There we go. 2 root 2 plus 2 root 2, which again is 3 root 2. So I get the same answer using a little good old-fashioned geometry, but you can see how the integral works. The point being that if we have a curve that does have a corner, and it might be something like this, we are going to use two separate integrals to get past that. If we have a vertical tangent line like we did with the cube root of y, we're going to rewrite it for y in terms of x and go ahead, or excuse me, for x in terms of y, and go ahead and use dy. All right, we'll do a few more of these in class, but that's it for the notes.